The search of bridge trees that I will discuss in next slide. So, okay, now since we have data qubits and we have Sydron rectangles, we are ready to search for bridge trees. The goal of this task is to find a small bridge trees. This is because the large bridge tree will need to deep measurement circuit, which in turn causes more resource consumption and leads to longer quantum error correction cycle. We prefer shorter quantum error correction cycle to reduce the effect of interference. Also, shorter quantum error correction cycle can lead to quicker fault-tolerant computation. So here to find the small bridge trees, we have to use two templates, the star tree and the branch tree. So as you can see in this example, to construct the star tree, we first find one node inside the Sydron rectangle and then connect this node to data qubits with the shortest paths. So this is one type of bridge tree we have found. Another type of bridge tree is branch tree. So in branch tree, we first connect each two data qubits. Then this will give us two branches, that is two independent trees. Then we connect those two branches with one path. Okay, now we get the finalized bridge tree. So with data qubits and the bridge trees fixed, we finally need to determine the execution order of measurement circuits. The constraint of measurement circuits scheduling is that measurement circuits that share qubits cannot be executed in parallel due to the resource conflict. So when there are many resource conflicts between measurement circuits, the execution order of measurement circuit will greatly affect the time of error detection. Overall, we hope to minimize the execution time of all measurement circuits. So to accomplish this task, we propose an algorithm refinement to optimize the execution order of the measurement circuits. So I don't cover details here, but you can look at looking in the paper for the details. Finally, for the evaluation, we consider 5 superconducting architectures that is from IBM, Google, Guerreschi computers. The main metric here is the error threshold of the implement quantum error correction code. So as you can see, quantum error correction code with higher error threshold can be implemented on more noisy quantum device and can have better capability to correct quantum errors. We also consider the computational resources consumed by the implemented source code by our framework. So for the error model, we follow the convention of quantum error correction papers, and we adopt the minimum with perfect measurement algorithm as the default. So here is the first evaluation result. So in figure present on the left, we show 4 quantum error correction codes. 2 of them are generated by our framework, and another 2 of them are quantum error correction codes by IBM. So as we can see, on higher hexagon architectures, our framework generated a subcode with a better error correction capability than IBM's code, while on the higher architecture, the code generated by our framework is still comparable to IBM. Therefore, we believe that it's the efficient design of error correction implementation rather than the sparse architecture that causes on satisfying error correction. That is, by adopting suitable compiling techniques, promising error correction is achievable even on low-weight devices.
I got it cut.
We also perform the resource analysis for our framework. The figure on the left shows the number of qubits used by our framework to implement the distance 5 subcode to superconducting devices. Here on the figure, ideal subcode refers to the case where no rigid tree is needed. The qubit consumption of our framework is within the quarks of ideal subcode. This indicates that our framework can implement the subcode on superconducting devices with relatively small resource overhead. In fact, we also perform the scalability analysis on our framework. That is, the resource consumption of our framework scales linearly with respect to the square root distance, just the same as the ideal system. Finally, to summarize, our framework provides the first compilation pipeline for implementing quantum error correction code on superconducting devices. This may motivate the research production for automated quantum error correction discovery and implementation. Secondly, our framework provides a baseline to compare with when researchers are designing new quantum error correction codes. They can just compare their codes with the subcode generated by our framework. Finally, we provide a test bed for evaluating the potential of a hardware in providing quantum error correction support. That's all. Thank you for listening.
Hi, this is Sophia from Chicago. I have two questions on the benchmarks used. One is sort of minor. Well, I know that the purpose of this paper is like surface code to devices with low connectivity. So I'm a little curious about why the square lattice is included in your evaluation section. Isn't square already the standard lattice for surface code? Why do you need those bridge qubits to map surface code?
Yes. For the square architecture, it also has a two implementation of the source code. Not only the one that without bridge qubit. You can also come up with another implementation with the bridge qubits. You can look into my paper for details. That is also the square architecture is also one currently usable quantum architecture. As you can see, Google's device is square architecture, right? So I need to include it to demonstrate the universality of our framework.
Wait, so are you saying that like, the way that you use bridge qubits to map surface code to the square lattice is better than like directly applying surface code to the square lattice?
Yes.
Yeah, look more closely at your paper, I guess. Yeah, and my second question is about, have you tried using benchmarks that are not uniform lattices, but like lattices that might contain some defects in it? I mean, codes like, due to like a failed link or a defective qubit?
Yeah, so currently we are focusing on currently usable quantum architectures. Because it's possible to consider other architectures, but it needs some motivation to consider the architecture that is not studied by the researchers. So it's a good question.
Yeah.
We may consider this in the future work. That is, when some like defects happen on the device, right? Hardware defects happen on the hardware. Also, like some new architectures that may appear in 10 years or in 5 years. Yeah, it's a good trend. Thank you.
Actually, what I was referring to was like, for example, a square lattice, but with a hole in it. Like there actually has been some papers that introduce something that they call the super operator. I mean, just a way to like use a larger syndrome to like isolate that hole. And I was just wondering whether your automatic approach could come up with some like other ways to work around that. Yeah, so it would be good to like, I don't know, test your algorithm on those lattices as well.
Hi, I'm Kate from Ishikawa. Great talk. I just had a quick question about the mapping procedures. There's, I think, a bit in the paper that you talked about how hardware was essentially even unused qubits or unused sections after the mapping procedures. Can you comment a little bit more about that and the relationship to the qualities of the chips?
Okay. Yeah, it's a good question. So you are asking about the relationship of the mapping and the underlying device.
Exactly. So there's a portion that discussed about how if you had when after mapping procedures, there were some portions of the chips that weren't used just because they're like extra qubits essentially. So kind of like building on Sophia's question of maybe if you had extra qubits that you could allow you to work defects as part of those extra qubits.
Yeah, it's a good question, but we haven't considered such cases that when device have defects or some other cases. Here we just assume the quantum architecture is present and we mapping to support on. And the key idea of mapping the circuit code onto such devices is that we can use the shape of the circuit code. And we match the shape of the source code on the device. So if the device is not perfect and it has some irregular shapes, so we need new techniques to overcome the problem.
Thank you. That's a good talk.
Let's thank the speaker. Hello.
Yes.
Next, we have Toucan, which is a quantum compiler for two local Qubit Hamiltonian simulation algorithms. The presenter is Browne, who's a physicist by background. He got his PhD from Imperial College London in 2004. And after 3 years as a junior research fellow at Oxford University, he joined the University of College London in 2007, where he's a professor.
Sorry, bear with me a second, there's a Zoom issue. Okay, thank you. Thank you for your patience and thanks for the organisers for putting this great conference together. So I'm very happy to speak to you about some joint work with Lingling Lab. Lingling was the first author of this work. Unfortunately, she couldn't travel here to present this because she's in China at the moment and the travel restrictions make it too difficult. I'm very happy to present this on her behalf. So what Jukan is an example of an application-specific compiler for a quantum computer. And there's been a lot of work recently on compilers for quantum computers, also presented here at ISCA. And there are a number of very prominent general purpose compilers. Probably most people in this room have at least experimented with using IBM Qiskit. And when you send quantum computations to the chips, there is some online transpiler compiler which is converting your quantum circuit into the specific lists of operations that are going to be realized on a quantum computer. So in this work, what we're looking at is a specific application, which is a very important, prominent application for quantum computers, the Hamiltonian simulation problem. So in Ken's talk, he talked about some of the most promising applications of quantum computers, and he also talked about some of the ways in which our current classical supercomputers are being used. And we think a significant chunk of those bars in Ken's bar charts is on the simulation of coherent quantum systems. So we expect this to be a very prominent early application of quantum computers. And so we want to develop compiler techniques which in particular target these important applications. And we're looking at a very specific example of a simulation problem, the Hamiltonian simulation problem. In particular, where we have some system that we want to learn about, and from our understanding of the properties of that system, we're able to write down a Hamiltonian. So the Hamiltonian is the quantum mechanical operator which represents the energies describing the system's behavior. So for example, it will represent all of the atoms in a molecule and all of the forces between them. And if we can write down that Hamiltonian, in principle, we can simulate it. So the simulation problem I want to particularly focus on here is solving the Schrödinger equation. So the Schrödinger equation, very famously, is the equation that governs the dynamics of quantum systems. And if the Hamiltonian is constant in time, it's actually a very straightforward differential equation to solve, and the solution is here on my slide. So we represent the solution by this unitary evolution operator U of t, which is just an exponentiated version of the Hamiltonian. So our question is, how can we realize this on a quantum computer? But actually, it's not necessarily so easy. I mean, in principle, so first we have to digitize the problem and represent it in terms of bits or qubits. And we do so by writing down the Hamiltonian in terms of qubit operators. And we commonly use the basis of Pauli operators. So these are the 4 operators at the bottom of my slide there. And if you form tensor products of these operators, this gives you a basis for the whole vector space of n-qubit operators. So you can write down any n-qubit operator as a weighted sum of these Pauli operators. And we call that the Pauli basis. So we're going to study the simulation of Hamiltonians represented in a Pauli basis, which are k-local. So k-local means that the Hamiltonian has terms in it where every Pauli operator has a weight at most k. So by weight, I simply mean the number of qubits on which the operator acts non-trivially. So for example, an operator x, y identity would have weight 2 because it's only operating on 2 qubits. So we have this expression for U of t, and you might think that would be enough, just take this matrix and feed it into your general purpose compiler. But there are a number of problems here. So first, this is an exponentially large matrix. Also, in principle, this could actually be any special unitary matrix. And typically the mapping to the basic components of your quantum computer, the single and 2 qubit gates, will be very complicated. But sometimes life is made easy for us. And this is this special case when the Pauli operators in our Hamiltonian all commute with one another. So we say that two operators commute when their multiplication ordering can be flipped without changing the value of their product. So what that means in practice is in a quantum circuit, we can rearrange the order of the gates without changing the computation. And in general, as is well known in quantum, when we work with quantum gates, the gates do not commute. So typically compilers have to be very careful to preserve the ordering of gates when they compile quantum circuits. Now, when the Hamiltonian terms commute, actually in terms of the sort of arithmetic of these operators, it's just pretty much the same as standard arithmetic with real numbers. And in particular, the exponentiated operator term factorizes simply the way e to the a plus b factorizes to e to the a times e to the b. And when it factorizes into these rather nice simple units, which we call Pauli gadgets. So these are these individual terms, e to the I times some angle times the Pauli operator times time. And it's very well known how to construct quantum circuits for such Pauli gadgets. They all have this very simple form, usually a ladder of C0 gates, perhaps a couple of other single qubit operations, and then a single Z rotation acting on one qubit. So in general, if we can decompose our computation into Pauli gadgets, it's straightforward to then construct a quantum computation. But the more interesting case is when the terms in the Hamiltonian do not commute. And there we can no longer simply decompose our U of t evolution operator exactly into these Pauli gadgets. But a very nice thing happens when t is small. It turns out we can write an approximation, which is sometimes called the Trotter approximation, sometimes also called the Lee-Suzuki-Trotter approximation, where we take our exact evolution operator and we approximate it as the product of these Pauli gadgets. And this is an approximation which is first order in T. To give you some intuition, it's very very similar to when you take a color wheel with all of the different colors, you spin it very rapidly. When the spinning is fast enough, the colors all average out and you will see the average color, which in this example would be the color white. And the same thing happens on the mathematical level when we construct these products of operators. But very importantly, there was nothing to tell me what order I needed to write the operators in. In the previous case, when they all commuted, the order didn't matter. But here now these operators do not commute, but nevertheless, we get the same level of approximation regardless of the order of these operators. So the order of these gates representing the Pauli gadgets will be arbitrary, even though the operators do not commute. So this really captures the main idea which Toucan is exploiting. It's a compiler which is designed to generate quantum circuits for the simulation of Hamiltonians using a Trotter approximation where we restrict our Hamiltonians to two local terms. And Toucan takes advantage of the fact that it knows the order of the gates in this Trotter approximation is arbitrary, and therefore it can reorder the gates in order to best, for example, reduce the computational depth of the circuit or to reduce the number of gates in the circuit. Now, we've restricted to two local Hamiltonians. Why have we done this? Well, first, these are a family of Hamiltonians of practical importance. They include physical systems such as spin chains, which are well studied. I mean, actually in physics, natural interactions between systems are always two-body. So if we're looking at simulating systems which are represented by represented well by qubits, they will naturally have two-body turns in them. And there are also some optimization algorithms such as max-cut QAOA, which can also be represented using two local Hamiltonians. And by restricting to the two local Hamiltonians, we gain the extra power to do additional optimizations which wouldn't otherwise be possible. So we're really interested in learning if we really focus on a very specialized set of problems, which are still very general and still cover a very wide range of computations that you might want to perform, how far can you push the extra optimizations? So this is a structure of a typical quantum compiler, and they usually have to perform a series of decisions, not necessarily in this particular order. So they need to make a decision about the qubit mapping, i.e. which physical qubits on the device will map to which logical qubits in the computation. They need to make a decision about routing. How are they going to apply swap gates in order to realize 2 qubit gates between qubits which are not directly connected on the device? Also, they need to perform some gate decomposition step where they transform the general unitaries in the computation into the specific unitaries that can be realized on the chip. And then there's a question of scheduling. How can you parallelize the operations, and what order should you implement them? So Toucan uses the fact that it's able to arbitrarily reorder the gates in these trotted decompositions at many stages of this compiler process. So I'll very quickly, you'll find the details of this in our paper, but I'll just give you some of the highlights of the sort of methods that we use. First, just to motivate it, so the aim of Toucan is to compile for a wide variety of quantum hardware, and we've already seen examples of this in some of the talks at this meeting. So the different devices which have been built so far all have very different topologies. So these graphs represent the layouts of qubits, and the edges on the graph represent possible 2 qubit gates that can be applied. But what has perhaps not been stressed yet in this conference is that often the gate sets are different between the devices too. So we usually speak about single qubit gates and CNOT gates as our basic default quantum gate set. But in many of the current hardware that's being developed today, CNOT gates are not the native 2 qubit gates. So here are some examples of the matrix forms of various quantum devices. For example, the Google Sycamore uses this strange gate, which is like a square root of an ice swap, if that means anything to you. The Rigetti chip uses an ice swap, and the IBM sort of realizes something close to a CNOT gate. So we would like our compiler to be able to compile directly into these hardware gates. And this is essentially what we want. So our input is our trotter approximation for our evolution. We can just think of this as a picture of just a series of 2 qubit Pauli gadgets. And the output is going to be a list of operations. So first, the mapping question. So we have to choose which physical qubit will represent which logical qubit. And the way Toucan does this, under the knowledge that it's going to be allowed to reorder all the gates, it simply looks at minimizing the distances between those qubits which are going to be directly interacting on the device. So we do that with a simple cost function, which just looks at each gate, looks at a particular mapping, and looks how far away are your qubits on the device with respect to this mapping, and it has a simple cost which is describing that distance. So this is a complicated combinatorial problem. We solve it via a heuristic using taboo search to try and minimize this. And essentially what you're doing is you're trying to put as many of the interacting qubits next to each other in the original mapping on the computation. Then you have to consider routing. So the mapping you've chosen initially has not put all of your interacting qubits in contact with each other. So you're going to have to add additional swap gates. And what Toucan does is it generates a sequence of maps, each of which is generated by adding a swap gate to the circuit. What that swap gate does, it rearranges your physical qubits. So it rearranges the mapping between your logical and physical qubits. And then once it has done that, it gathers together all of the remaining gates, which have now become neighboring in the new mapping. And so at each stage, it's reordering the gates using the freedom that we have in this trotter decomposition to have an arbitrary order. Now we also use some properties which we gain, some advantages we gain from focusing on 2 local Hamiltonians. So this means that all of our input unitaries in our circuit are all 2-qubit Pauli gadgets. And the swap gates are also 2 qubits. So what we do is we unify together all 2-qubit gates acting on a particular pair of qubits. Again, we can do this because the ordering is arbitrary. We unify them together into a single 2-qubit unitary because we have not yet performed our gate decomposition. I'll skip over the scheduling due to timing. So at the end, we perform our gate decomposition. We've gathered together all of these nearest neighbor 2-qubit gates, but at the moment they are not decomposed into the hardware gate set. But this is a further advantage of this toucan approach, is that only at this final stage do we apply the gate decomposition. And now we can directly decompose into the native gate sets of the device. So this is something which very few other compilers can do. Typically, they will they'll perform the gate decomposition quite early in the compilation process, and then only at the end will they take their CNOT gates and then decompose those into the native gates on the hardware. So I'm nearly out of time, but I'll just give you an overview of some of the results. So overall, the results were very good. I mean, as you'd expect, compared to a general purpose compiler, which can't perform all of these optimizations, and in particular, a general purpose compiler will always preserve the ordering of non-commuting gates. Toucan gives you significant advantages. And we also tested it against some other application-specific compilers, which have some but not all of the optimizations that we've been able to consider. The reason is because they have slightly different targets and are unable to perform some of these optimizations because of the slightly more general targets. So there's a compiler which is targeting QAOA optimization problems, and the polyhedral optimizer, which targets circuits made of Pauli gadgets in general, but not restricting to 2-qubit Pauli gadgets. So here's a lot of numbers on this slide, but each of these numbers represents the factor of improvement which Toucan gave us compared to 2 of the general purpose compilers, TQET and Qiskit. And this is in terms of computational depth, in terms of the number of 2-qubit gates, and you see the improvements are significant. We also tested Toucan on IBM hardware, and we benchmarked it against both some of these general purpose compilers and some of the specialist compilers. And we found again that on this hardware, Toucan gave the best performance. And in particular, for those of you who are experts on QAOA, we're particularly pleased that this is a rare example using Toucan of running QAOA on current hardware, where a 2-layer QAOA actually gives you a better performance than 1-layer QAOA. So 2-layer QAOA should always give you better performance. As you add layers of gates, you should get better performance in QAOA, but because of the additional noise, typically you actually don't. So we're very pleased to see this example of being able to exploit the full power of 2-layer QAOA and actually improve the performance due to these optimizations. So to conclude, we have developed this application-specific compiler focusing on these particular family of simulation problems which have several properties which allow us to sort of aggressively optimize. One of them is the fact that the ordering of the gates is arbitrary, and the other is that in the input circuit, all the gates are 2-qubit gates. So there's a lot of interesting future work to develop this idea further, extending it beyond the applications that we focused on. I think one interesting question is that given that our compiler is an approximate compiler, we've actually changed the unitary circuit that's being implemented. So it raises the question, how do we actually verify such circuits? If we had a very, very complicated quantum computation performing an approximate compilation, how do you verify the correctness and the performance of this and the degree of approximation in practice? I think that's an interesting thing to consider in future work. So to conclude, I'd like to thank our funders and also draw your attention to GitHub, where you'll find open source code of the compiler, and you can download it and have a play with it yourselves. So thank you very much for listening.
Thank you, Dan. We have time for one quick question, and the next speaker can make their way out here.
I'm Ali Javadi from IBM. Thank you so much for a nice talk. I just had a quick question regarding the last thing you mentioned. So can you imagine scenarios where under some other approximations where actually choosing the order matters?
Yes.
And like how the compiler might exploit this to sort of choose an optimal ordering or an optimized ordering?
So there's a very good question. So there have been some examples where the ordering is important. So recently there's been some very nice work looking at reducing this approximation error by randomizing the order. And if you sort of sample from an appropriately chosen random order, you actually improve your error rate. Now, unfortunately, in that scenario, we can't use toucan because the ordering is fixed. Nevertheless, the order is in some sense randomly chosen. So what we think it should be possible to sort of exploit not quite complete freedom to randomize your order, but some of the sort of limited freedom in the sense of the random samples of different orderings that are being used there. We think it should be possible, and it's on our roadmap, but it's not something we've looked at yet. But it's a very interesting and intriguing application of this because, yes, it does reduce error, and it sort of feels like it almost has the properties that we need for our compiler. So, yeah.
Thank you.
Yeah, let's thank the speaker. Thanks, man. Okay, the next talk is XQsim, which is modeling cross-technology control processors for 10+K qubit quantum computers. And the speaker is Ilkwon Byun, who's a fourth-year PhD student at Seoul National University. His research interests are cryogenic computing and quantum computing. Yeah, he's trying. Sure. No, go to the Zoom.
Oh,
Go to Zoom.
yes, but first turn on the presentation.
Yeah, it's turned on.
Okay. My laptop stopped. So share my screen.
Yeah.
Is it going well?
Yeah. Okay. Great.
Okay, let me start my talk. Hello, my name is Ilkwon from Seoul National University. In this talk, I will present XQsim, modeling cross-technology control processors for 10+K qubit quantum computers. This work is done in my fellow student and my advisor, Professor Zhang. We also collaborate with the research group at Gushu and Nagoya universities. Quantum computing is a new computing paradigm, which can innovate various areas with the quantum nature. However, to realize the potential, practical applications require hundreds of logical qubits, and we again need hundreds of noisy physical qubits to build one logical qubit. Therefore, we need a large-scale, fault-tolerant quantum computer with more than 10,000 of physical qubits. To build a large-scale quantum computer, we need a scalable QC interface and quantum control processor. In the superconducting quantum computer, QC interface controls and measures qubits by applying microwaves through analog cables. On the other hand, quantum control processor performs all the essential operations related to the fault-tolerant quantum computing. First, the scalable QC interface design is already actively explored. For example, the analog cables are the scalability bottleneck. The 4 Kelvin QC interface has been proposed to utilize scalable interconnects. However, a scalable quantum control processor has not been actively explored yet. Therefore, we target to propose a scalable quantum control processor architecture in this work. Before diving into the scalable design, we first introduce two key operations of the quantum control processor. In this talk, we focused on the surface code, where a logical qubit is built with a physical qubit patch. The physical qubit patch consists of two types of physical qubits, data qubit and Angela qubit. The first key operation is the error syndrome measurement called ESM. ESM indirectly extracts the data qubit error information by using Angela qubits. For this purpose, ESM entangles the Angela qubits with their adjacent data qubits and then measures them. The obtained Angela qubit measurements are called error syndromes. Note that to periodically find the errors, the quantum control processor should iteratively generate ESM instructions for every physical qubit in parallel. The second key operation is the quantum error correction. First, when X or Z error occurs in data qubits, the adjacent error syndromes are flipped. Second, the control processor identifies the error types and location by pairing the flipped syndromes. This step is called error decoding. Finally, the control processor corrects the identified errors by virtually applying X or Z gate. Note that the quantum control processor should support fast error decoding to prevent a system failure. In summary, quantum control processor should provide huge instruction bandwidth and fast error decoding. However, the two requirements limit the scalability of today's quantum control processors. Specifically, today's quantum control processor is not scalable for three reasons. First, there is no scalable microarchitecture for fault-tolerant quantum computing. Second, it operates at the room temperature. The increasing instruction bandwidth requires more 300 Kelvin to 4 Kelvin data transfer. The cables dissipate significant heat inside the power budget limited 4 Kelvin domain. Third, the slow CMOS technology can incur a huge decoherence error due to the slow error decoding or low instruction bandwidth. To resolve these problems, researchers propose various ideas in all the three directions. First, they propose scalable microarchitectures for several fault-tolerant units. Second, they propose the 4 Kelvin operation to eliminate the heat-dissipating data transfer. Third, they propose a superconductor-based SFQ technology, which can utilize ultra-fast and low-power voltage pulse. However, these ideas may not improve the control processor scalability. First, recent research with limited microarchitecture coverage may not resolve the real scalability bottleneck. Second, the 4 Kelvin operation can even degrade the scalability due to its huge 4 Kelvin device power consumption. Third, it is not trivial to design a scalable SFQ circuit due to its pulse-driven nature. Therefore, we need a scalability analysis tool to evaluate various emerging ideas in all directions. So our major research goal is to develop a scalability analysis tool for quantum control processor. First, the tool should support all the possible microarchitecture, operating temperature, and device technologies. Next, as its output, the tool should derive all the scalability metrics and the manageable qubit scale of the target control processor. With this goal, our research proceeds in 3 steps. First, we implement a full microarchitecture for quantum control processors. Second, on top of the microarchitecture, we develop a scalability analysis tool. Finally, by using the tool, we propose a scalable quantum control processor architecture. From now on, I will introduce our microarchitecture implementation. This is the overview of our quantum control processor microarchitecture. In RTL, we implement all the necessary hardware units for the fault-tolerant quantum computing. For the detailed implementation, we target surface code lattice surgery and develop custom compiler and quantum ISA. Note that this is the first full implementation of microarchitecture, ISA, and compiler, which can run an arbitrary quantum program with lattice surgery. Due to the limited presentation time, we will briefly explain only the key role of each microarchitecture unit. First, patch decode unit identifies the target physical qubit patches. Then, Patch information unit provides or updates the target patches information, which is the key to identifying dynamically changing target qubits. With the patch information, physical schedule unit schedules instructions only to the target qubits. Time control unit sends the scheduled instructions to the QC interface at the accurate timing. After the ESM is applied, error decode unit identifies the data qubit errors. Next, Pauli frame unit tracks the identified error for the virtual error correction. Finally, logical qubit measure unit performs all the complex operations related to the logical qubit measurement. In fact, our microarchitecture is really complex as shown in the figure. Specifically, we implement every microarchitecture unit in detail to support all the necessary logical operations, including the lattice surgery. Please refer to our paper for all these details. From now on, I will introduce XQsim, our cross-technology quantum counter processor simulation framework. This is the overview of XQsim. XQsim consists of XQestimator and XQsimulator. First, XQestimator predicts the frequency and power of each microarchitecture unit for various temperatures and device technologies. Next, based on the frequency and power, XQsimulator runs a cycle accurate simulation and reports the manageable qubit scale and the scalability bottlenecks. Let me first introduce our XQestimator CMOS model. We build our model on the existing cryogenic CMOS model, so-called CC model. CC model predicts the performance of hardware units running at 300 Kelvin and 77 Kelvin. For the 4 Kelvin CMOS model, we extend the MOSFET and wire model's temperature coverage to 4 Kelvin by using the recent 4 Kelvin measurement. As a result, our XQestimator can derive the frequency and power of both 300 Kelvin and 4 Kelvin CMOS units. Next, let me introduce our SFQ model. First, for the target control processor, the SFQ specific circuit synthesis generates the SFQ gate netlist by applying 3 features: splitter insertion, path balancing and clock network generation, and timing gap minimization. Next, by taking the netlist and RSFQ gate library, our model estimates the frequency and power of 4 Kelvin RSFQ control processors. For the ERSFQ, we apply twice higher dynamic power and zero static power to the RSFQ design by following the previous works. We validate the SFQ model with the post-layout designs using ICE process library. The right figure shows our validation results, which well matches the post-layout results for all the target designs. Therefore, we conclude that our SFQ model accurately predicts the frequency and power of quantum control processors. Next, let me introduce our XQsimulator. XQsimulator takes the XQestimator's output as its input and runs a cycle accurate simulation for the target quantum program. As a result, it reports the 4 scalability metrics and the manageable qubit scale. Also, it reports the logical qubit state distribution, but because it integrated with a noisy quantum simulator. To validate the functional correctness, we compare the logical qubit state distributions from XQsimulator and Qiskit logical qubit simulation. For benchmark, we run QAOA, QFT, and PPR with thousands of physical qubits. The right figure shows our XQsimulator's validation result, which well matches the ideal logical qubit simulation result. Note that this is the first to validate the fully implemented quantum control processor with the large-scale quantum simulations. From now on, by using XQsim, we will design a 10+k qubit quantum control processor architecture. In our case study, we explore 3 quantum control processors in chronological order. Systems with 300 Kelvin CMOS, 4 Kelvin RSFQ, and 4 Kelvin ERSFQ. We first analyze their scalability bottlenecks and then provide architecture designs to resolve them. For the workload, we run random Pauli product rotations. Please refer to our paper for the more detailed setup. First, we analyze the current quantum control processors with 300 Kelvin CMOS. In the right top graph, the red horizontal line indicates the scalability constraint for each metric. First, we observe that the current control processor scalability is lower than 250 qubits due to the slow error decoding. Specifically, our baseline EDU, or QEQool, sequentially moves the token to the next flip error syndrome and incurs significant delay. Therefore, to resolve this challenge, we propose a fast EDU architecture with the direct token setup. Our EDU directly allocates the token to the next target EDU cell and achieves 40 times EDU speedup. As a result, the scaling limit from EDU latency significantly increases to 9,800 qubits. However, the 300 Kelvin to 4 Kelvin data transfer now limits the scalability. Therefore, as our next step to reduce the data transfer, we decide to explore the control processor with 4 Kelvin RSFQ technology. First of all, rather than moving all units to 4 Kelvin, we move only PSU and TCU. This is based on our observation that PSU and TCU dominate the inter-unit data transfer while consuming much less power than others. However, we also observed that just moving PSU and TCU cannot improve the scalability due to the huge 4 Kelvin device power consumption. Therefore, to resolve this challenge, we propose low power PSU and TCU architectures. First, the key idea to building low power PSU is to share the fast RSFQ-based modules for many qubits. Specifically, as the mask generator inside PSU is 14 times faster than its CMOS counterpart, we can reduce the number of mask generators by 14 times. Next, for the low power TCU, we designed the RSFQ-friendly microarchitecture. Specifically, as the multiplexers and demultiplexers incur significant overhead in RSFQ, we design our TCU without using them. As a result, we significantly improve the scalability to 4,600 qubits. However, as the 4 Kelvin power is still the scalability bottleneck, we should further reduce the 4 Kelvin power consumption. Therefore, we decide to explore the control processor with much lower power ERSFQ technology. Now, we start our analysis by applying ERSFQ technology to the previous system. However, we cannot meaningfully improve the scalability due to the slow EDU. Therefore, we first additionally move EDU to 4 Kelvin for 14 times faster ERSFQ-based EDU. However, when we move EDU to 4 Kelvin, we cannot improve the scalability again due to the huge 4 Kelvin power consumption for its per qubit EDU cell. Therefore, to resolve this challenge, we propose a low power EDU architecture with the patch sliding scheme. The key idea is that we can share the constant number of EDU cells for all physical qubits because error syndrome pairing only occurs within the adjacent patches. Therefore, we significantly improve the scalability to 59,000 qubits. That is, we successfully achieve our goal, designing a 10 plus K qubit quantum control processor architecture. This is a summary of our architecture design. Note that this is just one of the possible ways for designing a scalable control processor. So you can explore your own architecture by using our upcoming tool release. I will summarize my talk as follows. First, we implement a full microarchitecture for a fault-tolerant quantum control processor. Second, we develop XQsim, cross-technology quantum control processor modeling tool. Finally, by using the tool, we propose a 10 plus K qubit quantum control processor architecture. Thank you for listening, and please let me know if you have any questions.
Thank you for the great talk. So we have time for one question while the last speaker can make his way to the podium. You have a question? Okay. Tirtha.
Can I ask a question? Yeah. So you showed that you perform lattice surgery for surface exposed with this architecture. Have you done some studies on how this architecture scales with the regard to code distance?
Yes, code distance, you're right.
Yeah.
Yes, actually, our current case study focuses on the code distance of 15, but our tool can support various code distance, and we show the functional correctness for every code distance. So if our tool will be available, you can test it.
Okay. All right. Thank you.
Yes.
Thank you so much, and let's thank the speaker.
Oh, yes.
I think he took the microphone. Yeah. You have the microphone?
Oh, you can't see on Zoom.
So Tirthak is an incoming professor at Rice University, and he's currently finishing up his PhD at Northeastern. He's advised by Deveshwari, and he has done work in quantum and HPC as well.
Thank you for the introduction. So I'm here to talk about our work called Geyser, which is a compilation framework for quantum computing with neutral atoms. And I worked on this work in conjunction with Dan Silver, who's a fellow PhD student, and our advisor, Professor Tiwari. So as we all know, quantum computers currently are promising, but they're very error prone. And there are multiple technology options. And a few that have been explored really well are superconducting qubits and even trapped ions a little bit. One other area of interest is neutral atom-based quantum computers. And the benefit of these computers is that they're able to have multi-qubit gates, and you're also able to have topologies which are, and you're able to have long-distance interactions, and you're also able to have topologies which have more connected qubits than you are with superconducting qubits. So in this work, we specifically look at developing a compiler framework for neutral atoms. So before we begin, a brief background. So as we all know, a state of a qubit is a superposition of the two basis states 0 and 1. And there are complex coefficients next to them, alpha and beta. And if we expand this to an n qubit system, we get a summation over all of the 2 to the n different states, and their complex coefficients add up. And the norm of their complex coefficients add up to 1, which basically gives us a probability of 1 when all of the states are summed up when we measure the states. In the context of neutral atom quantum computing, there are 3 specific gates that we'd be taking a look at. One is the U3 gate, which is a universal 1 qubit gate where we can apply rotation on a qubit and put it in any superposition. And for the 2 qubit and 3 qubit gates, we'll be looking at the CZ gate, which is very similar to the C0 gate, but the difference here is that instead of the last sort of bottom corner being flipped, we have the 1 being -1. And the way that C0 gate is generated from CZ gate is by twirling it with Hadamard gates. And then the CCZ gate is same as the CZ gate, but now it has 2 control qubits and 1 target qubit. And with neutral atom computers, we'll be able to apply the CCZ gate directly to the qubits. And that's why it's sort of significance here. And the model of quantum circuit that we'll be using is similar to the one that we've seen, where we have single qubit rotation gates being applied. And then we have the 2 qubit CZ gates with 1 control and 1 target qubit. And then the 3 qubit CCZ gates with 2 control qubits and 1 target qubit. So the overall flow of neutral atom quantum computer is as follows. We have our quantum circuit, and we send a circuit through a quantum compiler, which applies optimizations and compiler level sort of layout and routing and mapping optimizations. And that is sent to the classical interface. And then this interface converts it into pulses, which are then applied to an array of neutral atoms. And these atoms interact with each other via several electromagnetic forces. And once our computation is done, we take a photograph of the atoms and detect their state, whether the atoms are in 0 state or the 1 state. So for single qubit rotation gates, we use the outermost valence electron of the atoms, and we work with its Raman transitions to put it in superposition of different states. But for multi-qubit gates like CZ gate and CCZ gate, we use what are called the Rydberg interactions, where the valence electron from the outermost orbit is sort of transitioned to the Rydberg state depending on its basic state. And then it's a sequence of 3 pulses for the CZ gate and a sequence of 5 pulses that are applied for the CCZ gate. And for these pulses to take place, the atoms need to be within a certain interaction radius of the control and the target qubits. So as long as they're within this radius, they can interact with each other. If they're outside of this radius, they cannot interact with each other. But they're not directly connected, and they don't have to be immediate neighbors either. So here's sort of an example of Rydberg interactions for this circuit. Here the atoms are arranged in a triangular grid. The circles are the qubits or the atoms, and then the lines are not really physical connections. They're just there to show that it's a triangular grid. And what we have here is we have 3 operations running. 2 are 2 qubit gates, which are CZ gates, and then the operation at the bottom in the triangle is the CCZ gate. And the red circle, the red big circles show their interaction radii. So as we can see, when the atoms are running these multi-qubit gates, they have a certain interaction radius because they're popped up to the Rydberg state. And because of this interaction radius, we cannot run other multi-qubit gates within this same radius. Other operations are blocked off from that region. And that's why the Rydberg interaction radius also doubles as a blockade radius, because we're blocked off from performing those interactions. In this specific example, we see that the 3 operations that are being performed are far enough from each other so we can run them in parallel. If they were close to each other, then we would not be able to run them in parallel. And then we'll have to sort of serialize those operations. So the goal is to be able to compile in a way where we can run these operations as much as possible in parallel, and also be able to run multi-qubit gates, as we'll see next. So here's an example of running a multi-qubit gate. We see the CCZ gate on the left, and then on the right is the decomposed version of the CCZ gate. So if we were to run it using 1 and 2 qubit gates, we'll have to apply a total of 26 pulses. But if we were to apply the CCZ gate directly, we would only have to apply 5 pulses. So it's in our interest to be able to take the decomposed versions of these gates and compose them into the CCZ gate so that we can apply the same operation with much fewer pulses. And that's exactly the goal of Geyser. With Geyser, we want to be able to achieve these 2 goals. So the first one is to be able to parallelize as much operations as possible. And then the second goal is to be able to compose the smaller gates into larger CCZ gate so that we can apply fewer pulses. So as an overview of the design, the first step is to map the circuit to the grid, the chosen grid. The second step is to block the circuit so that we can serialize or parallelize as many operations as possible. And then the third step is to compose the smaller gates into larger gates. So let's look at the first step in detail. The first step is to map the circuit to a physical qubit layout. Now, typically one can use, so with neutral atoms, the atoms can be arranged in any grid. So we would be able to arrange them in a square grid, a triangular grid, a hexagonal grid. Experimentally, we found that the hexagonal grid was not very optimal because of how spaced out the atoms are. So the 2 options that we looked at were the square grid and the triangular grid. In the square grid, we see that if we want to be able to apply multi-qubit operations, then we would be able to do the CCCZ gate, which is 3 control qubits and 1 target qubit, but then it would block out 12 qubits from the radius around it. Whereas with a triangular grid, we would be able to apply the CCZ gate, but it would only block out 9 qubits around it. So empirically, we found that it was better to use a triangular grid, even though the square grid gives us the option to do larger gates. The triangular grid has fewer blockade and it enables us to parallelize more. So whatever the circuit is, whatever the algorithm circuit is, we map it onto a triangular grid. The second step is to apply the blocking step, which is to make sure that when the operations are applied, they can be parallelized as much as possible, and they're outside of each other's interaction radii. So in this blocking step, we start from the front of the circuit, and we use a greedy approach toward forming the blocks. So what we do is we start at the blocks where we can cover as many operations as possible. And the metric that we want to maximize here is the number of pulses, because as we form larger blocks with many more pulses, we'll also then later on be able to compose them into 3-qubit gates with fewer pulses. So we'll be able to get a larger optimization that way. So we start with the blocks from the front of the circuit, and we try to form blocks that can run in parallel and that are as large as possible in terms of the number of pulses that they cover. So visually, it looks like this. Let's say in the figure on the left, we have the first block already formed, so the first triangle in the far left, and we want to be able to figure out what block to form next. So we cannot do the immediate triangles near it because those are blocked by the interaction radius. But we have 4 other options. We can do triangle 1, 2, 3, or 4. And as the figure shows, we can apply those perfectly fine because their interaction radii do not overlap with each other. And we'd form the one which allows us to have the most number of pulses covered within that block. And if we look at several steps of this, we can go from sort of the red group of blocks to then the blue groups to the yellow group. And each of those cover different sort of regions of the circuit, because we'll be able to first parallelize the red group, apply it all together. Then we go to the triangle group, the blue group, we apply all of them together. And then we move on to the yellow group and apply all of them together. So whatever operations are not covered in one group, they'll be covered either the next or the third time. So typically this is how the arrangement would be laid out. And then the next step is to take these blocks and compose them into 3-qubit gates if they don't already have 3-qubit gates. So in our case, we use a composition method that is based on the unitary distance. We look at the distance that the original block and the composed block are from each other. And we're able to lower this distance by applying any sort of black box optimization. So here we have our original block. And then we have a composed block, which has 6 1-qubit rotation gates, which are flanked on either side of the CCZ gate. And there are multiple parameters to optimize here. So the rotation gates have 3 parameters each. And then the CCZ gate also has 1 parameter actually, and it's an integer parameter. It's to decide where the target should be and where the 2 controls should be. So we have that composed block, and we try to optimize these parameters together so that the distance with the original block's unitary is minimized. And we try to keep it very fine here so that the approximation is not too coarse-grained. We want to keep a very fine approximation. So if these many parameters are not able to optimize it to a level where the distance is within the original block, then we add another layer, and then we try to optimize those parameters. If that's not enough, we add another layer. And in general, the more parameters we have, the more degrees of freedom we have in terms of optimizing the blocks. So at the end of it, we'll be able to have a composed block which has hopefully fewer pulses than the original block, because now we've added 3-qubit gates to it. And that's basically the entire technique. So first step is to map to a triangle grid. and then to block it in a way that we can parallelize as much as possible. And then the third step is to compose into 3 qubit gates. So let's look at some evaluation results. So the first result that we look at is actually the TVD, which is the reduction in the error rate. For this, we use, so this is based on simulators, and we use realistic parameters from the neutral atom devices that we have right now. So the first bar is the baseline results. The second bar is Optimap, which is where we apply optimal mapping procedure, but we don't do the blocking and then the composing. And then the red bars are Geyser. And as we see the total variation distance, which is the difference in the probability distribution, the ideal probability distribution and the observed probability distribution is reduced anywhere between 25 to 60% points. So we were able to get pretty good results with this. And the reason for this is that, as expected, Geyser was able to reduce the total number of pulses in the circuit and also the depth of the critical path in terms of the number of pulses. So the figure on the left shows the reduction in the total number of pulses, and the figure on the right shows the reduction in the total number of pulses in the critical path or the total number of depth pulses. And we see that for both of these metrics, the reduction can be anywhere between 20 to 60%. And lastly, this figure shows further analysis of the results, where the topmost figure shows the number of U3 gates in the final circuits. The middle figure shows the number of CZ gates. And then the last figure shows the number of CCZ gates that Geyser was able to generate. So because it's able to generate CCZ gates, it's able to reduce the number of CZ and U3 gates. As we can see from the bottom figure, for some algorithms, it's able to generate many more CZ gates, while for some other algorithms, it's not able to generate any CZ gates. And for those, the reduction in the number of CZ and U3 gates would be next to nothing, and the results are close to Optimap. But for most algorithms, it is able to generate enough CCZ gates so that it can reduce the number of pulses and the number of pulses in the critical path. There are more results in the paper comparing Geyser to superconducting qubit technology using the simulation parameters from that technology, also about the complexity in terms of time and space, and then the simulation with different levels of noise as neutral atom technology progresses. And the last thing I want to say is that Geyser is open source here. And if you have any questions after this presentation, you can email me at that email.
Yeah, thank you, Deepak. You can do a quick question as you just like dismantle.
Sorry?
Yeah, you can have a quick question, but I think you should just start removing the equipment.
Okay.
Because...
Hi, this is Henry Wang from MIT. So I'm curious whether this framework can also be applied to, say, missing neutral items in the, say, preparation of the initial state.
Sorry, I didn't hear.
I mean, the missing atom in the grid. So is that will impact the combination process?
I still didn't catch the question.
Are you asking about the missing, if atoms go missing, if there's atom
missing
loss?
of atom in the grid. Yeah.
Sorry, can you repeat it?
So I think he's asking about atom loss.
Yeah, atom loss.
And how you would handle that if you have some atom loss.
Oh yeah, so in terms of atom loss, we use the same technique as the one that was proposed actually in last year's ISCA from Professor Chong's group about replacing the atoms at the rate possible. If it's not possible, then we're still able to do this composition step. And it's sort of remains the same technique. It doesn't really affect the technique. It's applied after you apply all these composition techniques.
Okay, thank you.
Okay, let's take more discussion offline. But yeah, thank you everyone. That's the end of the quantum session. Yeah, let's thank all the speakers. Sorry for